folks, we are taking the part 4 of our exercise 4.1. We were continuing with the principle of induction. We had seen that we do it in 2 steps. Step 1 where we show that P of 1 is true, and step 2 where we show that P of k plus 1 is true when P of k is true, and then together by induction we are able to show the mathematical statement. So this is how we were doing our problem, the problem till now. Now we are going to take up the problem number 7, and stay on the board. It says that it is 1 into 3 plus 3 into 5 and so on till 2n minus 1 into 2n plus 1 equal to what they ask us to show. So as we have done in all the previous cases, we will start with the proof. Let Pn represent the given mathematical statement. Step 1 to show that P of 1 is true. I told you earlier to get P of 1, first term from left hand side, and on the right hand side wherever n comes they will substitute 1. So we are going to get it like this, like the LHS would be like 1 into 3, and on the other side it is 1 into 4 into 1 squared plus 6 into 1 minus 1 by 3. Here the LHS is 1 into 3, which is 3. And let's check what is the RHS. 4 into 1 squared is 4. This is 6. So that becomes 9. 6 plus 4, 10 minus 1, 9. Divided by 3, it's 3. So LHS is equal to RHS. P of 1 is true. Now, assume P of k is true. How to get P of k? Wherever n is coming, there we are substituting k. So you'll get 1 into 3 plus 3 into 5 plus 5 into 7 and so on. 2k minus 1 into 2k plus 1 is equal to k times 4k squared plus 6k minus 1 by 3. To show that P of k plus 1 is true, so we have to frame it. Now how to frame it? We will have 1 into 3, 3 into 5, all terms till the kth term. And then the k plus 1th term. So how do you get it? Wherever k comes, put k plus 1. So this will come to 2 times k plus 1 minus 1, which means 2k plus 2 minus 1. So it is 2k plus 1. So your very first term will be 2k plus 1. The next term will be 2k plus 1. So k, wherever k comes, where we are substituting k plus 1. So it is 2k plus 2 plus 1, 2k plus 3. Now what's the RHS? Wherever k comes, k plus 1. So here also, it's quite a bit of work. Wherever k comes, there we have to substitute for k plus 1. So it is 4 times k plus 1 the whole squared plus 6 times k plus 1 minus 1. So that is k squared plus 2k plus 1. That is k plus 1 squared. So it will be 4k squared plus 8k plus 4 plus 6k plus 6 minus 1. What does that work to? 4k squared, 6 plus 8, it's 14. 14k plus 6 plus 4, 10 minus 1, 9. So the next bracket is 4k squared plus 14k minus 9 divided by 3. We've got to show this. Now in order to show this, let's consider the LHS. And let's see how it works. In the LHS, we've got 1 into 3, 3 into 5, so on. We reach till 2k minus 1 into 2k plus 1. The next term is 2k plus 1 into 2k plus 3. So this, because we know this result, we can substitute directly. It is k times 4k squared plus 6k minus 1 by 3. And the last term, it is 2k plus 1 into 2k plus 3. There's not much option left rather than expanding and doing it. So we will go in for an expansion. We'll see that the denominator we may have to equalize. So let's see how this goes. We can expand this also. 4k cube plus 6k squared minus k. And how does this expand? 3 times 4k squared plus 6k plus 2k plus 3 by whole over 3. So we have 4k cube plus 6k squared minus k. This is 12k squared. This is 18k. Then 6k, 9 by 3. Let's club these terms together. 4k cube, 6k squared and 12k squared. It will become 18k squared. And then 18 plus 6, it's 24, and 24, and then yeah, 18 plus 6, it's 24. 24 minus k, 23 plus 9. Yeah, plus 9 by 3. Alright, so we have to then check whether this is splitting up like this or not. And then only we are able to get this expression. So from here itself we get a hint that k plus 1 is a factor. Since we have learned the division in the earlier classes, we will just check if we are able to divide this. So let's take this over here. 4k cube plus 18k squared plus 23k plus 9. Let's try and divide with k plus 1. The quotient here is 4k squared. So 4k cube, when we multiply it, 4k into 1, it is 4k squared. Changing signs, this is going to be 14k squared. And the 23k comes down plus 9. And here now what can be quotient? It can be 14k. So 14k squared plus 14k. So when we change signs, we have 23 minus 14, that's 9k. 9k plus 9. So that is plus 9. That will give you 9k plus 9. Remainder is 0. So that means that these are the two factors. So this will come to k plus 1 times 4k squared plus 14k plus 9 by 3. And that's exactly our RHS. So LHS is equal to RHS, and therefore P of k plus 1 is true. From steps 1 and 2, given mathematical statement is true by PMI, principle of mathematical induction. So that is how we go about doing problems like this. Now obviously we'll be taking after the 7th problem, we're quickly going to take the 8th problem, and let's see how that works. So let's take up the problem number 8 and see how we can go in for its working. We had learned earlier that these are all very tailor-made, so it's only these in-between steps that you need to substitute. The remaining written part, it's going to be the same everywhere. Whatever, depending upon the question, these intermediate steps are going to change. That's all. So we are taking the 8th problem. And what does the 8th problem say? It says that it is 1 into 2, 2 into 2 squared, 2 into 2 squared, 3 into 2 cube, and so on. N into 2 raised to n becomes equal to n minus 1 times 2 raised to n plus 1 plus 2. Quite interesting. So let's see now how we can go about doing this. Absolutely same way. Let Pn represent the given mathematical statement to show that P of 1 is true. For getting P of 1 is true, we will be having the first term from here, and on the other side, wherever n comes, there we are putting 1. So let's see now what you have to be doing here. 1 into 2 to be equal to 1 minus 1, 2 raised to 1 plus 1 plus 2. 1 into 2, it's 2. And what happens here? 1 minus 1 is 0. So 0 into anything is 0. So it's like 0 plus 2, which is 2. Like that you have LHS equal to RHS, and therefore you have P of 1 is true. So that is done. Now P of k is true. Wherever n is coming, there we are going to put k. So let's see how it comes. 1 into 2 plus 2 into 2 squared plus and so on. N into 2 raised to n. Sorry, k into 2 raised to k is equal to k minus 1 times 2 raised to k plus 1 plus 2. P of k plus 1 is true. Wherever k is coming, there we are going to substitute k plus 1. So first term is k into 2 raised to k. After that you have the k plus 1 term. And then on the right hand side also, wherever k is coming, there we substitute k plus 1. So first term will be k plus 1 plus 1, k plus 2 plus 2. You need to show this. So let's take the LHS first. There are terms like 1 into 2, 2 into 2 squared, and so on. K into 2 raised to k. The next term is k plus 1 times 2 raised to k plus 1, out of which the result till here we know. It is k minus 1 times 2 raised to k plus 1 plus 2, and that term. K plus 1 times 2 raised to k plus 1. So what happens? These both are like terms. So we can club them together. When we club them together, 2 raised to k plus 1 is common. So it goes out. What remains here? K minus 1. What remains here? K plus 1. What happens as a result? The plus 1 minus 1, they are cancelling each other. And we are left with 2 raised to k plus 1. 2 raised to k plus 1 into 2k. K plus k, it's 2k plus 2. So we are fast approaching the result because this plus 2 already we have got. Now we have to get this. Out of this k is also already there. So you have to get 2 raised to k plus 2. So you have already 2 raised to k plus 1 and 2 raised to 1 here. A raised to m into a raised to n we have learnt is a raised to m plus n. Like that, this will come to 2 raised to k plus 1 plus 1. That is 2 raised to k plus 2 times k plus 2. That's our RHS. And that's how we get LHS equal to RHS. So P of k plus 1 is true from steps 1 and 2. Given mathematical statement is true by PMI. So this was our problem 7 and 8. We will be taking up the next problem in the next part.